Very good, thank you. Appreciate the opportunity to talk to you a little bit about MomentiveTechnologies and some of our approaches to some of the challenges in wide bandgap materials. So, first of all, I'm going to give a brief company overview, tell you a little bit about our interesting history, and then talk a little bit about tack coatings for silicon crystal growth, PBN electrostatic chucks, silicon carbide ion implantation, and then round it up with some BN BN as a thermal filler in electronic packaging. All right, so we're an advanced materials company. We're focused primarily in the semiconductor space. We're about 85–90% of our revenues are in semi. We produce a significant number of materials for the silicon processing space as well as the wide bandgap. In particular, our quartz crucibles, of course, are primarily for Czochralski growth. Our quartz products are used in all of the different areas for wafer processing, wide bandgap, and silicon. And of course, our solid products are machined into just about anything that they need a chunk of quartz for. The top outline there, the CVD coatings, heaters, electrostatic chucks, and powders are going to be the primary focus of my talk today. So we do have 4 manufacturing areas, or actually should say we have 4 countries that we currently manufacture in, USA, Japan, China, and Germany. And we also have sales offices in Korea and Taiwan. So, as mentioned, for this discussion, we'll be focusing on the high power challenges of wide bandgap materials and some of the challenges that arise from the production and the use of these materials. So as I mentioned, we've got a pretty broad portfolio in the wide bandgap semiconductor space, starting off with some of the crucibles, the tantalum carbide coated products we use for ingot growth, the tantalum carbide wafer carriers we use for the epitaxial of silicon carbide, various heaters and chucks that we'll talk about for the wafer processing, and of course the thermal fillers that go both into TIM1 as well as other packaging applications. We've been serving the compound semi industry for 20–25 years at this point, and we do, as it's shown, go through the entire value chain. All right, so let's talk a little bit about silicon carbide crystal growth, in particular our tack coatings. So obviously this is a pretty harsh environments. We're doing, in the industry, we're doing PVT. This is 2400 degrees C, partial vacuum, pretty nasty, aggressive chemistry going on there. And the CVD side of things for the epitaxial growth isn't much better, right? We're talking 1600 degrees C, under hydrogen, silane compounds in there, lots of reactions, lots of potential reactions with the silane compounds and any of the exposed material. So really you're looking for protective coating that can withstand this environment. So the answer for that, in our view, is the tantalum carbide. So the tantalum carbide that we produce and sell is a fully dense polycrystalline conformal tack coating. It effectively protects the underlying graphite and prevents contamination of the crystal, whether it's Epi or PVT, by the graphite. You can see some of the images here showing some of the cross sections as well as the nice conformal nature of the tantalum carbide. Plus it's pretty, right? When we first started doing some of this work, we did some testing to see how well it impacted the crystal growth. So this is looking at, obviously you're growing the boule of silicon carbide, and you can do that in a standard graphite environment, or you can have the tantalum carbide environment. And so you see here, again, oops. There you go. You can see how the wafer, the boule is grown, and we're taking the selected pieces, and this is numbered sort of reverse from the way I would have done it. But the wafer 3, 2, 1, all right, so wafer 3 is grown first and then all the way down. Then they just sliced out. And you can see in a standard graphite pot that you've got this exterior ring here of polycrystalline material. And it gets sort of worse and worse as it gets further down inside the boule. On the other hand, a tantalum carbide crucible prevents any of that secondary crystallization from occurring. And you get essentially a single crystal across the entire wafer. So you can also look at the defects within the crystal on those cross sections. You can see that made with a graphite crucible, you end up with a lot of carbon inclusions, defects, etc. With a tantalum carbide coated crucible, there is a micropipe shown in the diagram, but honestly the industry's gotten away and figured out how to prevent those for the most part as well. So now you can make very, very high quality tantalum carbide crucible, silicon carbide crystals, in particular using a tantalum carbide coated crucible. One of the benefits of this really has been in going to the 200 millimeter. That's shown to be quite advantageous as you step up. So even folks that were at 150 millimeters getting away with pure graphite are shifting to more tantalum carbide coated as they go to the 200 millimeter. All right, so now our PBN products. So PBN for us is pyrolytic boron nitride. And here we're going to talk about how we use this PBN electrostatic chucks in silicon carbide ion implantation. So one of the challenges with silicon carbide processing in particular is that it requires higher temperatures to actually do your ion implantation properly. Right? So you're up here in the sort of 500 to 700 degrees C range to do proper ion implantation. Competitive materials like ALN, right, would drop off in resistivity as you get to those temperatures. The resistivity is important because if you're trying to make an electrostatic, a JR, particularly electrostatic chuck, you need to tailor the resistance of that top coat to make sure you get good chucking forces, right? And so our PBN coatings have a very high intrinsic resistivity, and then they can be doped to achieve a lower resistivity. Of course, we can control this doping, and of course, that allows us to sit nicely within that resistance band that you need for JR chucking. So between these two materials, we can end up with operating temperatures of 400 to 1,000 for a standard PBN, and with our carbon doped versions, you get from room temperature to 800 degrees C. So PBN, why PBN? So it's got a lot of unique properties that make it really attractive for these type of applications. As I mentioned, it's got this very high but tailorable electrical resistivity. It also has very high thermal conductivity and very good thermal stability as well, which combine to give it very good thermal shock resistance and chemical resistance. It also ends up having a low dielectric constant, but because we do this process via CVD, you end up being able to make pretty much any shape of heater. These are all different heater forms that you can imagine, right? So fully three-dimensional. So obvious applications are in sputtering, ion implantation, CVD, MBE, thermal evaporation, lots of different options. So how do we really use this to our advantage in a heater? So we start with a graphite core, and then we'll put on a PBN base coat, right, which is nothing more than an insulating layer. Then we'll put on a series of pyrolytic graphite layers on the top and on the bottom. On the bottom, we'll put the heating element, and on the top, we'll put the chucking elements, right? And then we'll cap all of that with an additional PBN layer, all right? And what this gives us is all of the benefits of this nicely tailored, unit. You'll see here, what this really allows us to do is very high thermal shock resistance and very high and very low thermal mass, which means you can heat this very, very quickly. So this is a 200 millimeter single zone electrostatic chuck unit that we heated at 23 degrees per second, right, up to 600 degrees Celsius, multiple times. Don't do this with ALN, right? This just works, it works extremely well because of the CTE match, the very high thermal conductivity of the assembly, and the material just fundamentally allows us to do this. So again, we can use this, obviously we're not going to run this at 23 degrees a second for a standard tool, it's more just an example, but we can also use it because of the high thermal conductivity within the material, it allows us to get fairly flat temperature profiles. So again, this is a single zone heating element, right? Electrostatic chuck heater at 640 degrees, 700, and 800 degrees Celsius, and you see we're holding about 7 to 13 degrees C flat. Right? Not bad considering that's a single zone. Obviously, we can pattern that. We can turn that into multi-zones. We can change the heating pattern on a single zone. We can also change the pattern on it, the voltage, and in fact, we can turn this into an entire module design. So within our business, we can do the thermal modeling and actually create heaters, electrostatic chucks, combination units, modules that will be drop-in replacements. All right, for our final area or topic, I'm going to talk about some of the BN as a thermal management material. So this is a different BN. So that's not, the other one I was just talking about was pyrolytic BN, formed by a CVD process. This is a powder BN. So it has a lot of the same properties. It's got a high thermal conductivity, high electrical resistivity, very high thermal stability overall, and low dielectric constant and loss. And so where this comes into play, so it's got a number of industrial applications, but where this comes into play for power electronics, it really goes into being used as a thermal filler for both TIM1 and TIM2 materials, and in PCB boards for that matter. So here's some of the typical properties of our BNs. If you notice, it's a fairly lightweight material, right? 2.2 grams per cc, and that's its true value, not the bulk density. Thermal conductivity of 300 watts per meter Kelvin. Again, as I mentioned, just like the PBN, graphite, those other ones, this is a high thermal conductivity materials. Volume resistivity, again, fortunately out of pure DI water, at 10 to 15 ohms per cc. Very good dielectric constant. But the other thing that helps in these applications in particular is the fact that it's a very soft material, right? So if you're putting it into your compounders and your extruders and your die fillers and all these other things, it's not eating up your product as it goes through. So what does it buy you? Well, here's an example against some spherical alumina. And by the way, spherical alumina has its own place, absolutely for sure. BN is a premium product, right? So in all of these, it's a question of what's your cost-benefit ratio on all of these filler materials. BN is very good, right? You can see here against spherical alumina. So on the bottom here, check this out. We've got our neat resin down here along the bottom. As you add your spherical alumina up to 40, 50, 55 volume percent, you get up to about 1.5 watts per meter Kelvin. With the BN, you surpass that at, what is it, about 25 volume percent, right? And just continues to go up from there. Like I said, it's also much less abrasive to the system. There's also potential to combine these, right? So you get the best attributes of both. As far as dielectric strength, again, BN is a very pure compound, so it has very good dielectric strength, and again, doesn't affect the breakdown voltage of the neat resin. So you're basically, again, you're holding to that spherical alumina because of some of the other impurities that it tends to bring along, tends to drop it a little bit. And similarly, if you look at the dielectric losses that are associated with these different fillers, the BN versus the spherical alumina, again, all of this compared to the neat resin, you can see that the BN really has no impact on the material. So again, exceptionally low dielectric constant, dielectric loss. So again, if you're going to put this right in TIM1, at high frequencies, high voltages, these things matter. But again, the key component here was how does it do it actually affecting the thermal performance of the system. So here we did a simple example, right? Nothing too complicated. This is a simple resistor acting as a heat source with both a die attach going down to a water-cooled plate and then a potting around the whole system. So first we did it with neat resin, right? That's shown here. Even at about 30 watts, you got temperatures of about 150 degrees Celsius. Now if we put in 40 weight percent BN just into the die attach, so this is keeping a pure resin over potting resin, but just putting 40% BN into the die attach, you get about a 72% improvement, right, You're down here at about 60 degrees at the same wattage. It follows this line. If you then go one step further and add the BN to the potting resin as well, you can get the drop that's shown here, which is about another 40%, 50% reduction in temperature by adding BN to that also, right? So again, it just goes to what are you trying to do, what are you trying to achieve, that you can, again, get heat out of the system faster. Again, particularly important around our power applications. And that's all I have for you today, so thank you.
So, question open the floor. Okay, let me ask you a question. I think nowadays, if we want to achieve a very good semiconductivity die attachment for all the power devices, you think the way introduces the best solution, or how do you compare with other existing one, like other sintering silver or some other solution?
Yeah, no, I think so. Again, the BN can be put into the various greases, potting compounds, epoxies, whatever you need to put it in, and it works very well. Obviously, if you can get away, if you're not in TIM 1, if you're in a different application space, and depending on your price point, you might find another more optimal solution. But the BN, gives you a lot of advantages for that TIM 1 space. I think relative to again 300 watts per meter Kelvin. Yeah, not too many other ones that are going to compete against that.
How about the cost?
So it is a premium product, right? There's no getting around that, right? But again, you can, and our customers do, right, tend to blend it with other additives as well, right? So you're trying to, get the best of all worlds, ideally. Obviously, you have some trade-offs that go along with that, but